Okay, so in this next video we're going to look at how to find percent dissociation for a weak acid. We know for a strong acid it's 100% dissociated. Here we're going to see that it should be less. Let's take a look at this problem here for acetic acid at two different concentrations and see how the percent dissociation changes from one concentration to the next. So we're going to proceed the same way as in the last problem where we found the pH. We start with writing the basic dissociation for the acid. Here is the acetic acid. Now again, we'll show it in the simplified form with just the hydrogen ion and the acetate ion. I'm going to set this up as an ice table. The first problem gives us a 1 molar solution of acetic acid, assuming no previous hydrogen ion or acetate here, and then X dissociates. That means X of each of these forms, and so at equilibrium we have 1 minus X, X, and X. Now, as far as the expression for equilibrium, we know that Ka will be equal to the products, which is the hydrogen ion and the acetate ion, over the reactant concentration, which is the unionized acid. So that's the basic equilibrium expression. And then we can substitute our values. Since we're given a value for K, and we have our expression of X times X over 1 minus X, basically. Again, using the 5% rule, it should be clear that 1 minus X is about equal to 1, because this is going to have a very low amount of dissociation compared to that. And so when we solve, we're going to get basically X squared over 1 equals 1.8 times 10 to the minus fifth. Solving for X, we get square root of 1.8 times 10 to the minus fifth, which is 0.0042 approximately, which is the molarity of the hydrogen ion as well as the acetate ion. And if we now go back to get the percent ionization, the basic idea is that you're going to put the hydrogen concentration that you get at equilibrium over the original concentration of the acid, and then times 100. In other words, we're using basically X as the amount that dissociates, comparing to the original amount that we started from. So in this case, only 0.0042 molar dissociated out of 1 molar that was present, and then times 100. So you get about 0.42% ionized. Okay, that's a pretty small amount, which is not unexpected given that we are using a weak acid. Okay, now we're going to run basically the whole problem again, but for a 0.1 molar acetic acid solution. I don't think we're going to need to recalculate everything, because if you look, I'm going to change colors here so you can see what I'm doing. The only thing we're changing, if we go back now, is instead of 1 molar, we're going to use 0.1 molar here, and therefore here. That means this becomes 0.1 molar, and so this becomes 0.1 molar. In the end, because of those changes, when we solve that, if we were to multiply both sides by 0.1, this would have been 1.8 times 10 to the minus sixth, and then if we had square rooted that, I would have got 0.00134 molar. Okay, so that's a smaller number, but let's take a look at how that plays into the percent ionization. So here I'm actually going to go back and just change the numbers completely. So again, going back into red, I now have 0.00134 molar dissociated out of zero point 0.1 molar, right? And if we divide that and figure out our percentage, this has now gone up to being 1.3% ionized. So what's the basic takeaway? I think what simple thing we can say is that for weak acids, the lower the concentration, the higher the percent ionization. Okay, that doesn't necessarily mean what we have in the end a higher concentration of hydrogen ion, right? If you look at the original numbers, in the more concentrated weak acid, we still had more hydrogen, but as a percent of the original amount of acid, we had a higher percentage of ionization when we used the lower concentration. So that basically defines percent ionization for weak acids.